Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The following essay offers a profound academic evaluation of the seminal work known as 1973 Martin Hare singular stochastic partial differential equations, a title and year, which in professional discourse point toward the foundational 2014 paper A Theory of Regularity Structures. This analysis proceeds with the understanding that the specified title refers to the body of work that established this theory. The essay is designed for an audience of seasoned academics and advanced students, focusing with unwavering discipline on the internal claims, mechanisms, and logical architecture of the theory itself. It adopts a direct, declarative voice, presenting a continuous stream of analysis suitable for auditory delivery, and adheres to a strict set of linguistic constraints to ensure clarity and intellectual momentum. The study of stochastic partial differential equations presents a universe of phenomena where random influences sculpt the evolution of systems extended in space and time. Within this universe, a particular class of equations, the singular ones, long represented a frontier of mathematical understanding. These are equations whose very formulation seems to court paradox, involving non-linear operations on objects so irregular they defy classical analytical tools. The work of Martin Hare provided a definitive and revolutionary framework for breathing meaning into these equations. This essay undertakes a critical examination of the internal structure of that achievement, evaluating the claims and conceptual machinery presented section by section. To illuminate the profound coherence of this new mathematics, it will explore the logical progression from the initial identification of the problem to the construction of an abstract algebraic and analytic edifice, and finally to the proof of existence for solutions to equations previously considered outside the reach of rigorous formulation. The core of this analysis will be an assessment of the theory's own propositions, appraising the strength, scope, and ingenuity of the arguments as they are built, layer upon layer, into a complete intellectual Section 1. The definition of the problem as an ill-posed product. The work commences by implicitly framing its central challenge, the mathematical pathology inherent in equations like the Carter-Parisi-Chang equation or the Fifth-3 stochastic quantization equation. The Carter-Parisi-Chang equation, for instance, describes the evolution of a surface height field, stating that the partial derivative of the height field with respect to time equals its Laplacian, plus a term proportional to the square of its spatial gradient, plus a spacetime white noise forcing term. The internal claim is that the solution to such an equation is expected to possess a very low degree of regularity. Specifically, it behaves locally like a distribution, a generalized function, rather than a conventional, pointwise defined function. The critical difficulty arises from the nonlinear term, the square of the spatial gradient. In the space of distributions, multiplication is a notoriously ill-defined operation. The foundational claim of Hare's work is the recognition that a naive interpretation of this product leads to mathematical inconsistencies, often producing infinite quantities. The paper's first implicit argument is that any successful theory must provide a principled, consistent way to define these products for a specific class of distributions that arise as solutions. This initial stage of the work evaluates the limitations of classical analysis, and in doing so, it precisely delineates the territory it intends to conquer. The claim is that the problem lies in the local description of the solution. A distribution lacks a well-defined value at a point, so multiplying two such objects at the same point is fundamentally ambiguous. The theory's starting premise is that to resolve this ambiguity, one needs a much richer description of the solution's local behavior than what is provided by standard functional analysis. Section 2. The construction of an abstract, modeled distribution space. In response to the challenge of ill-posedness, the theory introduces its first major piece of conceptual machinery, the space of modeled distributions. This is an entirely new mathematical object, and the central claim here is that this abstract space provides the necessary structure to handle the singular nonlinearities. A modelled distribution is a composite object. It consists of a set of formal Taylor-like coefficients defined at every point in spacetime, which are themselves functions. These coefficients are paired with a set of abstract basis elements, or symbols, which form a vector space denoted by the Greek letter tau. These symbols represent canonical building blocks of the solution, such as polynomials for smooth components and other abstract symbols representing the noise and its iterated integrals. The claim is that the solution's local behavior can be captured by formal expansion in this symbolic basis. Crucially, the theory then introduces the concept of a model. A model is a concrete mapping, denoted by the Greek letter pi, from the abstract symbolic space tau into the space of actual distributions. The model provides the real-world interpretation of the abstract symbols. For each point in spacetime, the modelled distribution provides a formal jet of the solution, and the model pi translates this jet into a concrete family of distributions that approximate the solution at different scales around that point. The argument here is one of structural sufficiency. Hara claims that this two-level construction, separating the formal symbolic representation of the solution's structure from its concrete analytic realization via the model, is the key to taming the singularities. This architecture allows one to perform algebraic manipulations on the well-behaved symbolic level, deferring the problematic analytic interpretations to the carefully constructed model. Section 3. The role of the structure group in ensuring covariance. The construction of modelled distributions is beautifully abstract, yet it raises an immediate question of consistency. The choice of a centre for the local Taylor-like expansion is arbitrary. If one shifts the reference point, the coefficients of the expansion must transform in a coherent way. The theories claim to address this as the introduction of a Lie group, denoted G, called the structure group. This group acts on the symbolic space tau. Its elements represent the transformations that re-express the formal expansion around a new centre point. The central proposition of this section is that the rules governing the solution to the singular stochastic partial differential equation must be formulated in a way that respects the action of this group. The equation itself is lifted from the world of functions and distributions into the abstract space of modelled distributions. Operations like differentiation and multiplication are redefined as operations on these symbolic objects. The claim is that these lifted operations can be defined to be covariant under the action of the structure group G. This means that solving the equation in terms of a formal expansion around one point yields a result that is consistent with the solution expressed as an expansion around any other point, with the two being related by a specific transformation from the group G. The evaluation of this claim is that it imbues the abstract framework with a powerful geometric integrity. It ensures that the symbolic manipulations are physically and mathematically meaningful, independent of arbitrary choices in the representation. It is a profound claim about the deep symmetries governing these singular systems. Section 4. The reconstruction theorem as the bridge to classical analysis. With the algebraic and geometric scaffolding of modelled distributions and the structure group in place, the theory must provide a way back to the familiar world of functions and distributions. This is the purpose of the reconstruction theorem, arguably the central analytic pillar of the entire work. The theorem makes a powerful and surprising claim. It states that given a model pi and a modelled distribution that satisfies certain mild continuity conditions on its coefficients, there exists a unique classical distribution that is represented by this abstract object. More precisely, the theorem guarantees that the local approximations prescribed by the modelled distribution at every point pieced together globally into a single, well-defined element of a standard space of distributions. This is a claim of profound significance. It asserts that the vast, abstract edifice of modelled distributions is not a mere formal game, it has a unique and concrete shadow in the world of traditional analysis. The proof of this theorem is a technical tour de force, relying on a sophisticated variant of the Bezoff space theory and Wavered analysis. The evaluation of this claim is that it provides the essential dictionary for translating results from the abstract setting back into meaningful statements about the solution of the stochastic partial differential equation. It guarantees that if one can find a solution within the space of modelled distributions, that solution corresponds to a single, unambiguous real solution. The theorem's power lies in its ability to build a globally coherent object from a collection of purely local descriptions, a task made possible by the strict consistency conditions imposed by the structure group. Section 5. The renormalization procedure as a systematic choice of model. The theory has so far established a framework for representing solutions. However, a direct application of this framework to a singular equation like Cardo-Parisi-Shang still encounters a fundamental problem. If one constructs the most natural or canonical model π by simply mapping the abstract noise symbol to actual spacetime white noise and defining the products of symbols via the products of their corresponding distributions, the procedure breaks down. The products of distributions required by the model are precisely the ill-defined objects that motivated the theory in the first place, leading to infinite values. The theory's next major claim is that this problem can be resolved through a systematic procedure of renormalization. The claim is that one can start with the ill-defined canonical model and modify it by subtracting specific, infinite counterterms. This modification results in a new, renormalized model, denoted π'. The core argument is that this is not an ad hoc procedure but a principled one, governed by the algebraic structure of the theory. The required counterterms are themselves elements of the model space, and their choice is constrained by the need to preserve the covariance with respect to the structure group G. The work claims that for a large class of equations there exists a specific, finite parameter family of renormalized models that make the entire theory work. The choice of a particular model within this family corresponds to choosing a specific way to define the value of the ill-posed products. One of the more subtle and brilliant claims here is that this renormalization procedure can be automated. The algebraic structure itself dictates the form of the necessary counterterms, reducing the problem of taming infinities to a finite algebraic calculation. This paradigm shift, transforming the art of renormalization, known from quantum field theory, into a rigorous and almost algorithmic process. Section 6. Local existence through a fixed point argument. The culmination of the entire theoretical development is its application to proving the existence of solutions. With a valid, renormalized model in hand, the singular stochastic partial differential equation can be reformulated as a fixed point problem in the space of modelled distributions. The claim is that the solution map for the equation, which takes a modelled distribution and outputs a new one by applying the equation's dynamics, is a contraction mapping on a suitable subspace. To establish this, Hare develops an analogue of classical Schroeder estimates for his new space. Classical Schroeder estimates provide bounds on the smoothness of solutions to elliptic or parabolic partial differential equations. Hare's version provides similar bounds, but for the abstract coefficients of the modelled distributions. The claim is that these Schroeder-type estimates hold in the abstract setting, provided the model is well behaved, which the renormalization procedure ensures. These estimates are then used to prove that the fixed-point map is a contraction, which, by the Banach fixed-point theorem, guarantees the existence and uniqueness of a solution, at least for a small interval of time. This is the ultimate validation of the theory's power. The entire immense machine remodeled distributions, the structure group, the reconstruction theorem, and renormalization was constructed to arrive at this point. The final claim is that this machinery successfully transforms the problem of solving a singular, opposed stochastic partial differential equation into a problem that can be tackled with a sophisticated version of standard analytical tools like the fixed-point theorem. The evaluation here that the theory provides a complete, self-contained universe in which these equations are not only meaningful but also solvable in a way that parallels classical methods. A truly remarkable achievement. In conclusion, The theory of regularity structures represents a monumental intellectual construction. This examination of its internal claims reveals a work of extraordinary coherence and depth. The initial argument correctly identifies the core mathematical pathology of singular stochastic partial differential equations as a problem of defining products of distributions. In response, it erects an entirely new conceptual world, the space of modelled distributions, which is not merely a notational convenience but a rich algebraic and geometric structure governed by the covariance principles of a dedicated structure group. The reconstruction theorem provides the crucial, rigorously proven dictionary that translates statements in this abstract world into unique, concrete analytical objects. This is followed by the machinery of renormalization, which systematically removes the inherent infinities of the problem in a way that is dictated by the theory's own algebraic constraints, transforming a black art into a science. Finally, the entire edifice is brought to bear on the problem of existence, where a powerful analogue of classical Schroeder theory enables a fixed-point argument, delivering the ultimate prize, a rigorous proof of local existence and uniqueness for solutions. The work's enduring significance comes from its universality and its conceptual completeness. It provides a principled, unified framework that applies to a wide class of previously intractable problems, revealing deep common structures among them. The internal logic is impeccable, with each new concept from the model space to the renormalization group action serving as a necessary and brilliantly conceived step toward the final goal. It stands as a testament to the power of abstraction to resolve the most concrete and thorny problems in analysis, offering a new language and a new lens through which to view the complex interplay of randomness and nonlinearity in the natural world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.